Okay. So,
James, do you
in the
mind
name of
muting?
God, James, yeah. In the name of God, the compassionate, the merciful. This is the first of our C++ sessions. I think I haven't still told you what the book of this series is going to be. But before I do that, there are two things that I would like to tell you. One of them is that these slides that you are seeing, they were prepared, as you can see here, they were prepared in, some 2 years ago, so they might be outdated. I'll tell you when they are. The other thing is that now this part of the module will go with a much faster pace than the previous one. In fact, I think a lot of what we are going to see here is only syntax, and so I don't want to bore you up. I think that we invested a good amount of time in the previous part with laying down foundations that we are going to use here. So you are well prepared to flash through the syntax. Now, okay. So this is the book. This is the second edition of a book called C++ Templates. It's by three people, faces of two of whom you can see on this picture. These guys are they know very well what they are doing, and the book is quite good. As you can see, the book is a bit outdated because the book is about a bit outdated. It was from 2017. Now C++ has had two standards in the meantime. There was C++ 20 and C++ 23, and the thing is that there has been major changes. What I'm going to teach you, the techniques that I'm going to teach you are to some extent outdated because the linguistic support in C++ for C++ metaprogramming has now improved by far, and that's out of need. So people have come to realize that there is a need for better language support, and the committee has finally, after a long time, acknowledged that need and acted according to that need. Now, I haven't still chosen a newer book because I don't know of a book that is of this quality. So I'm hoping that sometime in the near future they will publish the next version, and the next people that I'm going to teach this to would not suffer from the outdatedness that you unfortunately are going to go through. Now, a bit of a warning. So these slides, they will be full of code. There is essentially little text other than code, but I will scribble over it. Given that these are my first slides ever, I will share them with you afterwards. And if you'd like, I can give you the annotated version or the original. That's up to you. Now, like I said, this is going to be a much faster Oh, someone has put something in the chat. I'm not sure I understand you, Daniel.
Oh, it's not important. I was just commenting on the cover art.
On the what? Sorry.
The cover art of the book.
Okay, I see. Okay. Right. So I can probably continue.
Yes.
Right. So I'm going to go much faster. Today, I'm going to, in one session, teach you 4 chapters. In the next sessions, I will teach you 2 chapters each. Now, this is only the introduction session, so I suppose that you can just help yourselves with the book. It's mostly syntax. And in a lot of what I'm going to show you, there is this what they pronounce this stud, right? It stands for standard, STD, right? You need to put that in front of the code that I am going to show to you in order for it to be compilable. But I'm not, I needed more space, so I just stripped those off. Now, so, okay. The first thing that I'm going to teach you is what in C++ is called function templates. These guys are, you have seen them in your previous languages. These are essentially functions that are type parameterized. So, for example, you have seen this guy, the max guy, right, which was a part of the ORD, and I'm deliberately leaving this part out for the moment, right? So this max thing took 2 things of any type. So the first, but now I'm pretending that these 2 types can be different, but they can't in the case of ORD, because ORD takes only 1 type parameter. Now, so it takes 2 parameters of 2 different no, actually they are the same, of the same type, and it compares them, and it based on the result of the comparison, it returns one of those, right? Now, if you want to do the same in C++, here is how you would do. So this is the syntax for type parameterization. So you put this extra thing at the very top, right? Just to say that, look, there is type parameterization. This is the name of the type parameter. And then you can, once you have introduced it, you can use it here and here and here and all that, right? And the logic is the same. Now, for the people who didn't know that, this itself is not quite a function, I had a simile. So I told them, look, this is like the mald, and it's not still a function. It will only become a function when you have provided the t, which means that when you have instantiated or specialized it for a special t, right? Now, a bit of a syntax at the very beginning. This type name, I hate it. Right. This type name thing that you get here, you can replace with class. That's not, I mean, I don't like that taste, so You will never see me doing that, but templates came to this world before type name was a keyword in C++. And in those days, they had decided that they were going to put class here.
Is it the same, or is there any difference?
Functionally, they are exactly the same.
Okay.
In this context.
Yeah.
Which means that if you put it, you know, these two are, oh, sorry. These two are exactly the same. Right? Everything that you can do with the one at the top, you can do with the one at the bottom, and vice versa. Right? Now, so now then there is the matter of instantiation, which I would tell to people, this is like pouring the liquid into the mold and getting it solidification. So the way you would do that is that you would pass arguments of the same type to this template function, and you would get the functionality that you would want. This is instantiation. And so at the top, that's about integers. This is now about doubles. And you can do that for strings. Right. So one thing to notice is that you know, there is type inference here. So you didn't need to provide anywhere in this the type int that you have up here, or double for this one, or string for this one. What is called the automatic type deduction is available, has always been available for function templates. And so in reality, this is more or less like the syntax, the Idris syntax that you can see at the bottom. Right? Now, so here is the simile that I often use with people. So here is someone doing some forging. You know, the ironsmith has first you know, done this bit. So they have designed the mold, right? Which in the case of C++ templates, this is like the definition of the function template, and then they pour the liquid into the mold. That's the matter of instantiation. And then once the instantiation is done, you can use that instantiated function, provided that it's successful, right? Provided that you can successfully instantiate the template. So right, this is to the left. Oh, to the left, it's the crafting of the mold. Is it mold? Wow. James, is it mold? Is it mold? I think, right?
Mold?
Yeah, mold.
Yeah.
Mold.
Mold.
Yeah.
It's not mound, it's mold. Yeah. Yeah, very funny. Yes. And then there is this to the right. There are these two steps. You can't actually disassociate at this point. There is a way to disassociate the instantiation from you know, using of the instantiated function, but I'm not going to delve into that for the moment. But so what you see to the right is both the instantiation and the usage of it, right? Now, okay, the C++ templates have a bit of what certain people consider anomaly. I don't think that is a good judgment of the procedure, but we'll go through the things that you might like or dislike, and you put of your own voting. Here is my take on that. So what is called two-phase translation for C++ templates is this. There is a question of what C++ deduces when, and what it detects when. In other words, which, long story short, which errors it detects when, right? So there are two phases where it detects errors, and some of it are detected in one phase. Some of the errors are detected in one phase, and some of them are detected in another phase, and there is a reason. So there is the definition time. If in the definition time you make a syntax error, let's say that you forget a semicolon somewhere, right? Then before even you trying to instantiate that template, C++ will tell you, right? That's you know, I have the simile here. So this is one instance. So let's say that there is a leakage at the bottom of the malt pot. Then you know, you will get caught even before, you know, pouring anything in it. I don't think that I need to go through all of these with you with the simile, because you guys are pretty seasoned with type parameterization. So I'll leave that out from here on. If you use names that do not depend on the template parameters, then C++ will tell you, wait a moment, I don't know what that is, right? So that's you compiling only the function templates definition, right? If you perform, again, static assertions, and we're going to see what a static assertion is, that don't depend on the template parameter, you will again, you know, get caught at the first phase. But there is the instantiation time, which finally all the template code is complete, and the errors, all the errors will be detected and reported to you. Now, what in particular you will not be caught for in the first phase, but you will be caught for in the second phase, is the parts that depend on the template parameters, right? This part would have not been available before because they depend on the template parameter. They can be wrong or right depending on what parameter what argument you pass for which template parameter. Now we're going to see examples, don't worry. So here you have a function foo that is parameterized by a type T, right? Now, if within the body of this function, you make a call to a function called, let's say, undeclared, which is, you know, undeclared, then you will get caught in the first phase, because the C++ compiler knows, even without you instantiating this, that you know, this function is undeclared, so it will stop you. But if there is another overload of the same name, which takes a parameter, and that parameter, now we have passed this t, which depends on this t, which is the type parameter. Right? If you perform this call, then you will only get caught at the second phase. Right? Now, so here is your first presentation of a static assert, right? If you want to assert that your integers are always larger than 10 units of measure, right? Then and these are bytes usually. Then this is a static set, which means that the compiler will try to validate that statement inside the pair of parentheses. I'm sorry. Right, the compiler will try to verify this the statement. This is not a statement. The expression, actually, this part of it only. During compile time, and if it finds out that the statement is the expression is not correct, then it will give you this error message. Right? Now, this one will fail at the first phase because it does not depend on the type parameter t. Whereas this other one, the second one, will be caught at the second because it depends on this t thing here. Right? Now, I think that this is a good time for the first joke. Daniel, give us yours, please.
All right. Let's see here. Yeah, I got a Norwegian one actually.
Okay, tell me. So is it in Norwegian or is it about Norway?
It's about Norwegians.
Okay, tell me.
Do you know why people from Norway are usually very good at Linux or editing files in Linux?
At doing what at Linux?
Editing files.
No, and I didn't know that they're so good. Okay.
Well, it turns out that their ancestors were actually Vikings.
Okay.
Very good. Very good.
I'll see myself out.
Good.
Okay. Okay.
Right. Down for a while.
Yeah, that was a very good one. Yes, that was a very good one. Yeah. Thank you. Okay, let's get back to work. So I told you about the fact that there is template argument deduction in C++. Now that's what helped you or helped the compiler to deduce, given this template function, function template, it helped the compiler to deduce in these cases the t's that you see here, right? However, there are intricacies involved. So, for example, if you pass 4 and 7.2, the compiler stops you and tells you, you know what? I don't know what t to put in because these are of different types, right? And I can't. Now I've already taught you unification. First yawn from. I'm going to write that down. Yawn number 1 from yes, yes, from Niels. Okay. So yeah, the compiler can't unify the t that it gets from this side and the t that it gets from this side. Now that's where why you get the unification problem. Sorry, the error message. By the way, the C++ error messages, they never tell you anything about unification. In fact, I am not sure about the compiler vendors and about whether they know what unification is, but it definitely is not a part of their terminology. You know, they use it all the time, but they don't use the terminology. So, but you know what's going on. Okay. Now, so the other thing is that, well, ordinary functions can have default parameters. So, for example, this function g has it takes an integer as its parameter, and it's saying that, well, if I ever wanted to make a call like this, then you, the compiler, know that the argument that I'm missing out is this 14 thing here, right? Now, you can do the same for function templates. The function templates can also have, default arguments, but the thing is that there won't be any there won't be any automatic type deduction based on the default arguments, right? So, for example, this call would have probably wanted to be f of string, and we'll go through this syntax, right? Which means that even though I am leaving out the argument, and the compiler is capable of picking up this default argument for me, it will not perform type deduction on the basis of that default argument. Now, Sander, did anyone have any questions?
No, I was just I found it weird that it didn't do the deduction, since it has all the information it needs.
Right, you were surprised about the failure of the compiler in performing. Right. Well, I'll get back to that, but I wanted to ask a question from Sander. Sander, tell me, why would the following fail?
What does it say there? Float?
Yes, float.
Is it because the default argument is a string?
Right. Okay, thank you very much. That's true. Well, this is called a string literal.
Yeah.
Right. And string literals have this type in C and also in C++. Well, don't worry if you don't know what that is at the moment. We'll get to it. Now, anyway, so the thing is that there is no conversion from this type to float. So even though this call is providing is explicitly providing the type that the compiler will fail to automatically deduce based on the provided default argument, the call is still ill-formed because of the lack of conversion from the default argument to the explicitly provided type parameter. Sorry, type argument. Right, and there is a technical difference in C++ between type arguments and type parameters. Some of you might already be familiar with the nitty-gritty about what's a parameter and what's an argument, but we'll get to that. So you do recall that with the previous definition of max, this call failed. So one way to proceed is to say that, okay, I want T1 and T2. I want the first and the second arguments to be of different types. And the way you would do that is that you would augment kind of what's inside the angle brackets. So this, by the way, in case you didn't know, this is called angle brackets, right? Now, so you would augment it with a larger list of the type parameters that you would want to put in, and then you know this thing, the logic is more or less the same. Now, I have put something underneath, which I call the Idris pseudocode. And I would like to ask Jan to tell me why this is only a pseudocode. Why is it not?
You don't have an ordering constraint.
That's part of it. That's true.
Could you repeat that, Jan? I couldn't quite catch what you said.
He doesn't have an ordering constraint in
Thank
part
you.
of his type declaration.
Right. Okay.
Also, T1, T2. You don't have a valid cast instance for B. You don't know if it's coercible from.
Okay,
A to B.
that's supposing that there is a cast, right? So supposing that there is a cast, what else is just pseudo here, and not quite.
Those were my two instant reactions.
Okay.
Ordering and meaning that you don't have a less
Well,
than, more than, and
well, I'll
supposing
give
you have
I'll
those
give,
two. Yeah, go on.
No. I'll give you leave this one out, right? Leave this one out. It's about the ord, right? And here is a hint. What was the syntax for using ord? Do you remember?
Gek, lek, and equals.
Right. So let's say no. This is what I'm asking.
Oh.
So you would say max is ord, and then
T1.
Right. So
yeah.
what would you put here?
Both T1 and T2.
So you would want to put or T1 or T2.
But those aren't of the same ordering.
Yes.
Necessarily.
So the thing is that this one allows you to compare two instances of T1. This one would allow you to perform comparison between two instances of T2.
But you can't compare between them.
That's true, right? So the thing is that ord takes one type parameter, not two. Right? So were you to put an equivalent Idris, then you would have wanted to have an orderly interface that compares between two types, not just one.
Or if we're assuming the cast, we can cast B. In the case.
That's it. Correct. So that's a different. If we were about to retain this comparison, right? Then you would have needed to, you know, provide a different ordering, right? Now,
Exactly.
now, here is something more subtle, and I'm going to ask this one from James. Let's get back to the C++ version. Now, James, why is there no constraint on the template parameters T1 and T2 in the C++ version with regards to you know, the orderliness of T1 and T2?
There doesn't need to be, because the less than sign is defined on the object, which will be instantiated. So you'll get a type error later in the second phase. So if you put two objects that couldn't be ordered, because it's a template, that will be a value error based on the template when it's instantiated. So there's no requirement to, there's no need to put that. It's sort of what the template becomes has that, not the template itself.
Right. Okay, that's true. Thank you very much indeed. Now, however, so if you do that was completely correct, right? But you know, if you instantiate max with two types, let's say that you instantiate it like this: max of 4 and string test, right? If you do that, now with that particular instantiation, there is no such comparison operator, less than operator defined, right? Now, at the instantiation, which is the second phase, as James correctly put, right? Then you will be caught for the compiler not being able to find the less than operator that you're using here, right? So before the instantiation, which is the phase one, this piece of code is innocent, is considered to be innocent, right? However, there lies a problem. The problem is that, let's say that your compiler, sorry, you're the vendor of this. This is library code. This is come on. I'm very picky about the shapes of what I write. Yeah. Now let's say that this is the and by the way, my handwriting is better than this, but given that I don't, I mean the keyboard is underneath my my wrist, I will have difficulty, you know, putting things on. Now let's see. Oh, I can do one. Right, no, oh no, sorry. Right, let me see. So let's say that this is your library that you are shipping to your user, right? Now this is your code that you're shipping, and then your user uses this library for their types, and then they unknowingly, you know, this is the inside part of your code, right? They don't know what's inside your code. They unknowingly pass two template arguments, or two arguments to the function template max that cannot compare, right? That do not compare. Then the error message that they get is actually, first of all, very big, right? Secondly, it points to this point in your code, not in their code, right? And so this is kind of, some people consider this irresponsible coding, and to some extent they are right, right? Because if there is a requirement on the input that your code expects, then that should be documented. And yes, of course, you can always put comments like T1 needs to be compared or needs to compare against T2, right? You can always do that, but it's, you know, this is not exactly what is required for shipment of the code, because you know, this is still expecting your user to read through your comments, right? Yeah, you can also, you know, do the triple so that you get them in Doxygen or things the like, right? But still, this is not the right one. What would be the right one would be that you put some sort of requirement syntactically to T1 and T2, right? Like, for example, how we do ORD in Idris, right? Now, that is how, after more than a decade of the standard committee of C++ banging their heads against the wall, they finally came to an agreement on what is called the C++ concepts. Now, I used not to teach you know, C++ concepts to people in this module, but you know, with you guys being so good, I'm thinking that, well, you have enough, so I might utilize the fourth session on teaching concepts to you. In short, concepts are the equivalent of the Haskell type classes, and more to it, equivalents of the Idris interfaces, right? Now, so had we had the type class, then we could have put a requires clause somewhere that we'll probably see later, so that we can enforce the availability of this guy, so that when our pool user of this library uses this piece of code, they get stopped at their instantiation site, stating it that, look, you have violated that requirement, right? And they get a very clear error message. Now, okay, you know, there is also support for the choice of the return types. So in the case of you know, this expression, we never know which one of A and B is going to win. Okay, that's yawn 2 by Mikhail. Right. Now, so you see, we don't know which one of A and B would win, right? So there is something here that is new, that is saying, well, I don't know what the type of the return statement or the return statement would be, right? Now you, the compiler, go figure that out. Now, sometimes the compiler needs a bit of a help, right? So you do put alter here, but in order to give it a hint, right, you put this arrow sign, well, and then you know, the type, the expression that you wanted to particularly focus on to the right of that arrow, to the right of that right arrow, right? Now, given that this, you know, this condition does not quite participate in the type deduction, the value of this condition does not participate in the type deduction, you can only put a Boolean of your choice here, for example, true, and say that, look, it will depend the exact value of the type that is going, sorry, the exact type that is going to be sitting here depends on a condition that is going to choose between A and B, and the value of that condition will be resolved at the instantiation time, sorry, at the runtime, but the value of that choice is not important. What is important is that there is a choice between A and B. Right? Now, Niels, is this something you can follow?
Yeah.
Okay, good. Right. Niels, would you mind sparing your joke, please?
My joke.
Yes. Yes. Okay, that was. I was about to tell you that you have a very unique sense of humor.
Yeah.
And I see you just presented that. Thank you. Okay. I hope the ones that are watching this in the future do also appreciate your unique sense of humor. I do. Okay. Now, let's see. In C++, you can overload functions, and operators are only special functions. So it is possible to, that there is the built-in plus operator that works between ints, right? And there is also the same operator that is overloaded for strings, right? That's an instance of function overloads. Operators are just special functions, and you can have two overloads of this function f, one of them taking no parameters, and the other one taking an integer as a parameter. And so then when you call f with a parameter I1, supposing that I1 is the one that you get here, which is of type int, then which one of these gets chosen? So which version out of the two is the one that is going to be called here? Anyone? The second one. Yes, that's right. Yes, that's right. Yeah. Thank you. So, okay. Now there's also overload. By the way, I didn't tell you what. There's a piece of terminology here. The matter of choosing the right overload by the compiler is what is referred to as overload resolution, right? So now we're going to talk about overload resolution in the presence of templates. So suppose that you have this function which is not type parameterized, and somewhere within the same compilation unit or available to it, you also have this other function, which is a function template because it's type parameterized, right? Now we're going to see a series of examples and decide why, in which of them which overload is chosen. That's us going through few steps of overload resolution, right? Now, if we get this one, by the way, as a rule, if it comes that the compiler gives the same weight to two overloads, it will produce an error message telling you that I don't know which one to choose. Right? Now, overload resolution is always based on the best fit. Right? If there is no best fit, the compiler will give up. Right? Now, and there is always non-template functions are always of higher priority than the template functions, than the function template. Sorry. Now, that is the reason why the one on line 9 is always a call to the first overload. And now, let's see. Sander, could you please tell me why on line 10 the overload that is chosen by overload resolution is the second overload? You're on mute.
Because it sees that it receives 2 floats as arguments, and since the first max on line 2 takes 2 integers, then it obviously can't be that.
Okay, that is true. That is true. But I'm gonna try to refute your argument by saying that in C and inherited from C to C++, there is silent type conversion from floating points to integers.
Okay.
Why were those double numbers not silently casted to integers, and then it would have been the first overload that would have been chosen?
Maybe because that step comes after looking for a template that fits. I'm not sure.
Okay. Well, fine. Let's leave it at that point. I expect that your answer will be ready by the end of this slide. Okay. Now, so if you choose to call the call on line 11, then with the same kind of line of argumentation, the compiler comes to take that to be a call to the second overload, for the t-type parameter being char. Okay. Now this one is a bit strange, I guess, to you, because it has this sign, which I think you are not completely familiar with. Now, what this is saying is that, listen, the compiler, I don't want to provide the type parameter, but I know that you, the compiler, can figure it out given these. And that's the reason why, even though these are integers, it's the second template parameter, sorry, it's the second overload that the overload resolution will choose, because we are enforcing the use of automatic type deduction for the template version. Right? Mikhail, are you lost?
I'm
No.
I'm following.
No. Okay, very good. Very good. Now, so now this call, the one on line 13, right? For the same reason, or for similar reasons, you know, the use of the explicit use of angle brackets with double in between is us instructing the compiler to use the second resolution, but this time there is no argument deduction. There's no automatic type deduction for the type parameter t, because we are explicitly providing that t to be double, right? Now, here is where we get to the what Sander needed to counter argue my argument for refuting his argument. So, if you were to perform this call, you get here an instance of the type char, right? And here you get an instance of double. Now, were you to be only bound to these two overloads, you are having one overload which is not type parameterized, and another which is type parameterized, right? Now, however, this type parameterized version only takes one type parameter, which means there is a need for unification between these two types, which is not available in C++. So what it does is that it takes a look into the alternatives, which do not require conversion, but it can perform conversion based on non-template type deduction, right? Now, in this case, this can decay, or it's the other way around. It's this can be promoted, so char can be promoted to int, and double can be decayed or demoted to int. Therefore, it can perform a call to max with int and int without any template type, without any type parameter deduction. That is why this one is always a call to the first overload out of the two. Any questions?
So this is like a pullback?
No, it's not a pullback. It's a presentation of a rule about the automatic type deduction, which says no casting upon automatic type deduction.
Okay.
So that is the reason why in this case
It costs him a double.
yes, right? That would have required casting, right? Whereas this does not require any casting.
The final one doesn't require any casting.
Correct.
Right.
Yeah.
Yeah.
Okay.
Because at that point it defaults to ints because both have ints.
That's right. That's
Yeah.
right. So
Yeah.
so the compiler can instantiate the second overload in the case of line 10. It can instantiate the overload perfectly for the type double. Right?
Both arguments are given as doubles.
Correct. But it cannot. Thank you very much. But it cannot perform that for the case of line 15. Yeah. All right.
Makes sense.
Now,
Thank you.
You're more than welcome. By the way, guys, we are going way slower than expected. And I'm not sure how much of this we would be able to do until the end of the session. But I hope I can really well, okay, if we can't go through all of it, then we'll need to have other thoughts. Let me just march on, and we'll see what's going to be in it. So now there is a piece of syntax in C++ that says, well, if the arguments that we pass for these two, in this very instance, for these two parameters are expressions that are completely available for evaluation at compile time, then I would like to have the result of passing like those two max available also at compile time. So for example, if I do things like this, this is the Euler number, right? So if I do this, you know, these two are compile time expressions. They are available to the compiler at compile time, right? It will not perform any runtime evaluation on them, right? We would like to be able to have the result of this entire thing, this entire thing available to us at compile time. The way to enforce that is by putting this const expr thing, you know, at the front. By doing so, we are saying that, you know, because this is available at compile time, I can have a C-style array based on that number, you know, and perhaps you know that you know, if I have let's say int n, and I read that n from the input, or whether I do that or not doesn't really matter. I will not be able to do sorry. I will not be able to do this, because n there will be a runtime entity, whereas if I do, let's say 80, if I do, then this is doable because 80 is a compile time expression. Now, in the same vein, this is also valid because, you know, this is a compile time expression because, you know, the arguments here to max are compile time expressions, and therefore, you know, the result of the comparison between the two compile time expressions is also compile time expression because there is a const expr here, right? Now, for the same reason, we can also pass the same expression as the second argument that we pass to the template, to the class template called array. And that takes us to class templates. Sunda, would you mind sparing your joke, please?
That I can. Why do fish live in salt water?
Okay.
Usually
don't
to
know.
breed and then return back into freshwater. Like, no, to live and then return back to breed into freshwater. That's the case with salmon.
Well, you're
Oh,
almost there. It's because pepper makes them sneeze. Yeah.
Thank you. Thank you. So we are done with function templates. This is awful handwriting. We are done with function templates. Now we would like to go through class templates. Oh, this is not keeping up with me.
Oh,
All right.
having some latency.
Yes. So here is a class which is for stacks. Inside it, it keeps the elements that it has in a vector, and you know, vector is this is not the Idris vector. This is kind of like a variable size array, right? It's a part of the STL, the standard template library of C++. You don't need to know much about it. What really matters is that you understand that there is some internal storage, and it provides the expected API. So it has a pop, it has a push, it has a pop, and you can also check whether the stack is empty. Now, what is there for you to notice is that this guy, the type parameterized class C, is similar, not quite equivalent to the familiar Idris that you get at the bottom. All right. So what it says is that given a type T, C will become a type. So this is higher kind, right? Now, and then you know you can put these member functions that we had provided here. So push, pop, and empty. You can either inline their definitions or put them outside. So here is, for example, them being outside. You know, there is a bit of syntax that you need to be careful about. You know, if you are providing a member function of a class called stack, which is type parameterized, then you need this leading extra bit of syntax. At the top level, what else? I think the rest you should read yourself. Right, and then you can, you know, you can instantiate the class template that you have. So, for example, you can have a stack of integers, you can have a stack of strings, and you can perform the push and pop and the top and empty and all that. Now, here is a bit of difference between this and what we saw on slide 6. Unfortunately, you know, in Remarkable, I can't jump from, yeah, the links don't work. So well, but the PDF that you will receive will have the links. So for the function, so what would have this been a function? I could have said stack of something, and if there would have been no argument passed, then I just put the open parentheses, close parentheses, and that the compiler would do the automatic type deduction for me. Now, automatic type deduction was not available in C++ before C++17 for class templates. There now is support for that, but the support is not exactly like that for function templates, but it's very close. So in this case, for example, you can't leave out the types that you want the compiler to instantiate your stack class template with, but there is a bit of hope. We'll get to see that. Now, let's say that we have this member function print on. Now, what happens if these operators are not provided for the element type of so what happens if those operators are not defined for T? And I'm going to ask that from Jan. Which phase of the compilation will the code fail in?
The the casting, I guess. Oh no, it would cast, and then it would fail at whichever one that checked for the operator.
Okay, let me remind you that templates enjoy this feature in C++, which is called two-phase compilation. So
yeah, that's what you're
and the first one is the one that does not depend on the type that is passed. The second one is the one that does depend on the type that is passed.
So then it would be the second one, since it needs the operator.
Yes. Yes. So the two-phase translation will only mean that this will only fail. So that line 9 will only produce an error message if the T that is used here does not support this this operator at the second phase, because that's the phase where
type is relevant.
Yes, that's right. Okay, now you can have what is called specialization, and so you guys being familiar with some of the programming languages terminology, people will use different names for these, but in that community, this is referred to as ad hoc. Come on, why did I forget the name? Ad hoc something, which I can't remember quite now. So yeah, this is anyway, this is considered to be ad hoc because what comes well, let me first explain to you the syntax. What this is saying is that, well, you, the compiler, know that there is a template, there is a class template called stack. It takes one type parameter, and now I would like to say what the definition of that class template is for the particular case where string is the type that is going to be passed. Right? Now, this is us giving a particular behavior to stacks of strings. Now, what is special and perhaps unexpected is that the behavior of stack of strings has nothing to do, needs not to have anything to do with stack in general. It can, in particular, have none of the. It is allowed not to have any of the member functions of stack. It can have its own completely different member functions, right? And that's where the ad hocness is from. You know, there's no relationship between the stack class templates in general and the stack of strings. Please, yeah.
Was the term you were looking for polymorphism?
Yes. Ad hoc polymorphism. Ad hoc polymorphism. That's right. That's true. So, okay. Special syntax again. Now this is us saying that look, stack has to be stack itself is type parameterized, but we are not providing that type parameter. It's here that we are specializing it. You know, the C++ syntax is awful, and I do apologize for it, but unfortunately that wasn't my choice. You know, and it was, I have to say that it was no one's choice. It was coincidental. You know, no one knew when they were giving this syntax to this piece of language. No one knew, had slightest clue that one day in the future templates would be used this way. You know, it's a long story. I will go through it as we go through the book. What else? Right. You can also perform what is called partial specialization. So you can have, for example, you can work a specialization for when you have pointers to T. Right? Now, you can see that this one still has a type parameter because it's working on every pointer to T. And where does T come from? Oh, it's a type parameter itself. Right? And then, well, the rest of the nitty-gritty syntax is on you to read. Now you can partially specialize in the presence of more than one template parameter as well. So provided that you have a class, my class, that takes two type parameters, you can partially specialize it so that there is a specialization for when the two type parameters are the same. Which means that if you instantiate my class with, let's say, int and int, right, then this would be the specialization that is chosen, and the syntax that is inside here has nothing, needs not to have anything in common with what the syntax that is in here. Right? Like the case of function templates, and in fact functions more generally that can have default arguments to the ordinary or value level parameters. Type level parameters can also have default arguments. Right? So now we are saying that, well, the elements are going to be stored in an instance of the second type parameter. Now we have added a type parameter here, which if the user of the class stack does not provide, we are going to be we're going to take for being Victor of T, which in that case will be the same as the previous version of stack that we have. Right? You can perform type aliasing. So for example, you can say that I don't like these angle brackets. So hereafter, when I say in stack, I mean stack of integers. and you know, you can even further simplify your job when there is a need. You know, instead of providing all these, you pass a single type parameter. So you could say deck stack of, let's say, string. Right, in which case, you know, it says, okay, this is you passing the right, well, one type parameter to deck stack. What is deck stack? Oh, it's when there is the t is this t, and deck of t is the container that you're going to use, right? Now here's the template argument deduction for class templates that I promised. So before C++ 17, if I wanted to let's say, so this is a stack of integers, and I want to have a second stack of integers, that I want to copy the first one into, or initialize, sorry, the right terminology is that I want to initialize the second one using the first one, right? That meant that I had to put stack of int here, but then with the available template argument deduction that is provided after C++ 17, I can leave out the stack of int here. So that I no longer need, because the compiler can figure out that type for me, right? Now you can also have what is called deduction guides. Now deduction guides, let's forget about the line 1 for the moment, right? Now deduction types are the ones that tell the compiler, look, I don't care about what you usually do. Here is what you do if you receive one of these special items, right? Now, this, I told you, has the type constant char star, right? Now, if it is that we want the compiler, in this case, in the case of line 3, to deduce the type of string stack to be sorry, to be stack of strings, then we can get help from the compiler by instructing it to say that, look, if I ever pass to you a string of const, well, you can also shuffle the ordering, but that's fine. If I ever pass to you one of these, so stack of one of these items, which is the same as these, right? Then you should instantiate that for a stack of strings, right? So the line that you see above, the line 1, is telling the compiler to pretend that that it has seen a stack of strings when it receives a stack of const strings. Sorry, const char pointers, right? And this pretension, it's not that it will instantiate the class string for this type. It will actually instantiate it for this one, but because there is an implicit conversion from this to this, the the deduction guide works. Right? Okay. Right. I should stop here. We are not going to make it. There's plenty remaining, so I just stop the share. Oh, someone had written something. What was the motivation for shifting over to C++ templates? Oh, right. Well, I wanted to show you that first of all, so maybe not everyone sees this question of Daniel. So Daniel asked, what was the reason for shifting from Idris to C++ templates, right? And the answer is this. First of all, I wanted to show you that language concepts are very related. So even though C++ and Idris were designed by very different people with very different mindsets, there are still loads of similarities between the two. This is one thing. The other thing that I wanted to show you was that C++ template metaprogramming is considered very difficult in the C++ community. I work for example, I work for this company called Entropy, that is owned by this multi-billionaire Russian, who is a C++ veteran, and is close to his retirement. He has always been very successful in selling his C++ companies, and he does still do C++ coding. He has never touched, in his decades of C++ programming, never touched C++ template metaprogramming, because it is considered, a lot of people consider C++ template metaprogramming overly difficult, and they just give up on it. And I think James's example, the company that he works for, is one of the companies that does not touch STL, and they are not rare. Unfortunately, they are not rare. Does not touch STL because they consider that to be difficult, right? And so, it's a matter of class. The C++ community sees as those who can do C++ template metaprogramming as the higher class people. It's and I want you guys to have that on your CV. I do C++ template metaprogramming. You better scare for me, right? And the third thing is that I want to show you that with the right theoretical foundations, with the right theoretical background, you will be able to defeat difficult things. So, like, I'm sure you guys will be able to go through C++ template metaprogramming much faster than the vast majority of experienced C++ programmers, because I have put a lot of effort into training you the concepts in a world where there is very little syntactic clutter, whereas in C++, the syntactic noise is absolutely high, right? Okay, no problem. I'm just gonna stop anyway. So I have a message from Macau saying that someone has booked the room that they were in. So I'll take it that we have to stop. I'm gonna stop the recording.